So, let's continue our next lecture. Let me just recall, last time we have defined concepts of three concepts we have defined last time. One, generating systems. For vector spaces. Let me also fix the notation today also like yesterday, that K be always field arbitrary and V K vector space. And last time we have defined these three concepts. Generating system for vector space V. 2, linear independence of an arbitrary family. Vi, I and I of vectors in V. And 3, basis for V. And the most important thing we will keep using is the following theorem what we stated last time. That, so I will write again completely because this is the most important statement for this subsection. Let V be a vector space and Vi, I in I be a family of vectors in V and let F be a map from K power round bracket I to V defined by any tuple AI I in I which is in K power round bracket I goes to the linear combination of these AIs, AI, VI. So, first of all, let me remind you that when we write K power round bracket I, we consider those tuples for which almost all AIs are 0. Almost all means all but finitely many tuples are components are 0, and therefore this sum when we write it makes sense because in this sum really only finitely many AIs are non-zero. So, the sum makes sense. So, we have a map from K power I to V. Then we have translated these concepts in terms of this map. So, 1 Vi I in I is a generating system for V if and only if the map F is surjective. This is simply a restatement of the definition of a generating system, because surjectivity means every element x in V is coming from some tuple. That means every element x has a representation of linear combinations in terms of Vs. Second, Vi, the family Vi is linearly independent over K if and only if F is injective. This is also immediate from the definition of linear independence, because linear independence means if a linear combination is 0, then each coefficient is 0. So, if some tuple goes to 0, then the tuple itself should be 0, and tuple 0 means all components are 0. Third one, now combining 1 and 2, by definition basis is a generating system which is linearly independent. So, Vi, I in I is a basis of V over K if and only if F is injective and surjective, that means F is bijective. And most of the time we will use this theorem, and beside that this will also give an, later on maybe we consider isomorphism etc. It will tell us that every vector space V is isomorphic to one of this type, but I will repeat this when time comes. Okay. So, now I want to see some examples. So, in these examples let us K always denote field, arbitrary. When I take the special cases of field, I will indicate that term. Okay. And so, first one, this is standard basis. So, let I be any, I will call it index set. Usually index set means the set which is used for indices, for enumerating the elements of some set. And consider the vector space K vector space K power round bracket I. Once again I will write here, these are all tuples such that almost all AIs are 0. These are the tuples in K power I. One can also think them as functions. F, not, I do not want to call F now. Functions phi from I to K, such that this condition will get translated phi of I equal to 0 for almost all I in I. So, we have seen in earlier lectures that this is a K vector space, and now I want to give some family here which we will test whether it is a basis, linear independent generating system, etc. So, for each I in I, we have the standard tuple EI. EI is, if you like, it is delta Ij, delta Ji. J is varying here, J is varying in I. So, think of this as a map from I to K, where I goes to 1 and any other J goes to 0. So, either you think as a tuple or you think as a map, and it is clear by the definition of EI only I goes to non-zero entry. So, EIs are elements in this k power round bracket I, and I want to prove that. So, we will check that E I in I is a basis of k power round bracket I. Okay, and this basis is called the standard basis. Of k power I over k. So, to check it is a basis, we need to check two things: it generates and the family is linearly independent. So, first we will check that A, we are checking that EI I in I generates k power round bracket I over k. So, this means we should check that elements of arbitrary tuples AI I in I k power I round bracket I is a linear combination of these EIs with coefficients in k. But note that this tuple AI is the sum AI EI I in I. This is obvious because when you first of all, sum on the right side makes sense because only finitely many AIs could be non-zero. And secondly, when you expand it and compare the components, it is clear that ith component in this right hand sum is AI, which is the ith component in the tuple AI also. So, therefore, these are equal, and this precisely means that any tuple in k power round bracket I is a combination of linear combination of the elements EI. Therefore, it generates k power I. Now, second thing we have to check that they are linearly independent. So, this is B. We have to check that the family EI I in I is linearly independent. Over k. That means we need to check that. So, we need to check. So, to check that if a linear combination of EI EI is 0, and again I will, so this AI tuple is in k power round bracket I. So, this means it is indeed a finite linear combination. Then we want to check that from this we want to check that all AIs are 0. This is what we need to check. But if you take, we have given this sum is 0. So, if we check what is the ith component in LHS is precisely AI. And so, if this tuple, this is a tuple, if this is 0, then ith component is 0, but then ith component is AI, so AIs are 0. So, this follows from that. So, we have checked that it is linearly independent, and therefore, EI, this family EI I in I is a basis of k power I round bracket I. So, you remember last time also I have defined a concept of coordinate functions with respect to a basis. I just want to recall. So, if we have as a basis of V, then we have defined for each I in I, we have defined functions from V to K by using this basis, and that we have called it Vi star. So, any vector x here goes to Vi star x. This is by definition ith component of the tuple ai in I, where the tuple ai is uniquely determined by this equation x equal to summation ai vi in I. This tuple is in k power round bracket I. So, because this is a basis, each vector x can be written uniquely in this form. So, this tuple ai has only finitely many non-zero entries, therefore it is here, and this coefficient ai is this is what map x goes to ai. So, this is called the coordinates of this vi x is called ith coordinate of x with respect to this given basis. And then we could have also written this as summation I in I Vi star x Vi. So, you see this the idea of writing this is it only depends on x and a basis Vi. Okay, so now in this in the above case, what are the coordinate functions with respect to the standard basis? So, coordinate functions the standard basis ei in I of the vector space k power round bracket I are what maps? They are precisely, so they are maps from k power I to k, and these are ei star, and these are precisely the projection map. This is mapped to ai. This is so ei star is precisely the ith projection. Okay. So, let us take a special case for when I is a finite set. Special case when I is a finite set and that to 1 to n. In this case, k power round bracket I is same thing as k power I, which is also sometimes we are denoted by k power n, which is k cross k cross k n times. This is the Cartesian product of k n times. And E1, now we have E1, E2, En. So, E1 is the first position 1 and then the remaining zeros. E2 is second position 1 and the remaining zeros, etc. En is the last position is 1, that is nth position 1, and everywhere else it is 0. So, this is a standard basis of k power n, and coordinate functions ei star or even star, let me say even star from k power n to k. This is the first projection. So a1 a2 an goes to a1 etc. En star is the nth projection, that is this a1 a2 an tuple goes to the last component an, that is nth projection. Okay, so this is the standard basis. The next example, example 2. If a family Vi of vectors in V is linearly independent, it may or may not generate V, but the linearly independent means if a linear combination of Vi is 0, then each coefficient is 0. In this case, we cannot say it is a basis of V, because we may not know that it is a generating set for V or not. But surely what we can do is, we can take now a subspace U. U is a subspace generated by this family Vas. That is, remember this notation we have been denoting like this, K Vi. This is the subspace of V generated by this family Vi. This means by definition it is the smallest subspace, the smallest subspace of V which contain all Vi's. And we have seen in earlier lecture that such a subspace has a nice description, that every element of that subspace is a linear combination of Vi's. So definitely now we can say that this Vi, I in I, is a basis of U over K, because by definition now U is generated by Vi's, and to start with Vi's they are linearly independent family. So this is a basis of Ui. Okay, now next I want to recall third one. I want to recall for future also a couple of remarks about polynomials. First about polynomials. After this I will come to polynomial functions. After this I will come to polynomial functions, and after that I will even come to rational functions, and after that even I come to many more interesting functions which will be very useful in analysis courses, for example. So let K be a field, and this actually one can do more generally, that you can even don't even need to assume that K is a field, but I will restrict in this course only the field. So everybody know what a polynomial is. A polynomial f in one variable x is an expression like this: a0 plus a1x plus an xn, where this x one usually calls it indeterminate. Or also call it variable, and these are the formal expressions. One can also think of them as a vector a0, a1, an and 0, 0, 0 after that. because I want to think this as an element in k power n. So if they are round bracket n. Note that only finitely many terms are non-zero, could be non-zero. And the last one where it is non-zero, if this is non-zero, then one calls that n as a degree of f. If everybody is 0, then the degree is not defined. So that is a 0 polynomial. So the 0 tuple corresponds to the 0 polynomial. This corresponds to f equal to 0 polynomial. 0 polynomial. So the degree of a 0 polynomial is not defined. This n is called the leading coefficient of f, LC of f, leading coefficient of f. And we know now how do we add polynomials. Add it component wise. So if you have one polynomial fx, and normally one drops this x in the notation of the polynomial, you will just call it capital F. This is a0 plus a1x plus an xn. G is another polynomial, b0 plus b1x plus bmxm. An is non-zero, bm is non-zero. This is n is the degree f, m is the degree f, degree g, and then you add f plus g, same as we have been doing it in this. Add it component wise and put that a corresponding coefficient. So this is a0 plus b0 plus a1 plus b1 x and so on. So it will depend on whether m is smaller or bigger and so on. So this is very well. Also you can multiply by a scalar. AF is clear how to multiply. You push that a inside everywhere. So that is, this is summation. This also one can write summation from I equal to 0 to n ai times x power I. So that's how we add polynomials. We also have learned to multiply polynomials. The multiplication of polynomials is rather complicated in the sense we first multiply the powers of the variable xi, xj, x power I plus j, and then use distributive law to expand. So that's how we extend this multiplication to the polynomials. So this will be summation ck xk. K is from 0 to wherever, m plus n here, and ck's are defined by summation ai times bj. This summation is running over I plus j equal to k. So these are the usual formulas for the polynomials over a field. And so therefore important thing to note is, note that this k, the set of polynomials, this I denote by k square bracket x. This is the set of all polynomials with coefficients in k. So on this set we have two operations. We have defined addition or multiplication. So with that it becomes a commutative ring with multiplicative identity, the constant polynomial 1, and the additive identity with respect to plus, the neutral element is the 0 polynomial. More than that, we also have a scalar multiplication. We also have a scalar multiplication on kx, scalar multiplication of k on kn. So, this makes this kx as a k vector space. And it is very trivial to see that the commutative ring structure and this vector space structure are compatible with each other. So, I will just say that the ring structure and scalar multiplication are compatible with each other. So, this means whether, so when one says ring structure, that means this binary operation plus and the multiplication, and scalar multiplication is the scalar multiple. So, whether you add first and then scalar multiply or scalar multiply, add and multiply, all these operations are compatible with each other. So, for us very important here now, I want to study, we want to study first, want to study the k vector space of polynomials, all polynomials. So, for example, extracting a generating set, or whether is it linearly independent, whether is it a basis, how many elements it has, etc., etc. And many subspaces which will arise from this space of polynomials. Okay. And before I end with the polynomials, important things to note here, which I will assume without proof. This is exactly similar to that of ring of integers. Like we have seen in case of ring of integers, fundamental theorem of arithmetic, prime numbers, division with remainder, Euclidean algorithm, GCD, etc., etc. That also makes sense in the polynomial ring. And the most important thing is like a what is called division with remainder. This is the root of many things. So, that is, if I have two polynomials f and g with coefficients in the field k, so k field is very important here. And if g is a non-zero polynomial, then I can divide f by g and write quotient and remainder. So, then there exist polynomials q and r with coefficients in the field. This q will be called quotient and r will be called remainder. So, that the polynomial f we can write it as q times g plus r with either r is 0 or degree of r is strictly smaller than degree of g. Note here, one has to be careful here, I have to say this separately because we have not defined degree of a 0 polynomial. So, therefore, this is necessary to mention, and also degree g makes sense because our assumption is g is 0. And now from this Euclidean algorithm you can go on, from this division with remainder we can go on to define what is Euclidean algorithm. You can define what is a GCD, you can define what is LCM, also you can define what are irreducible or prime elements. Exactly as we did in the case of integers. So when I say a prime polynomial, that means irreducible polynomial with leading coefficient 1. Leading coefficient 1. The last remark, and we will have a break. The units in the polynomial ring Kx are precisely non-zero elements in the field, that is we are denoting by K cross, and this follows easily from what we call it a degree formula. If I have two polynomials, degree of f times g equal to degree f plus degree g. For f g in Kx, both non-zero. This is very easy to prove because you look at the product and look at the coefficient of x power n plus m, and it will be a coefficient of x power n in f and coefficient of x power m in g, and so both are non-zero. So the product will be non-zero because we are in a field. So let us have a break and then we will resume soon. Thank you.